Hello, everybody. So today we're going to continue our discussion in Chapter 2, Section 6. And in the previous video, I showed you how to compose two functions, which is to take one function and put it into another function. What I'm going to show you today is how to decompose two functions, which is the exact opposite of what I showed you yesterday. Yesterday, we were taking two functions and we were combining them into one. Today, we're going to take one function and we're going to tear them apart and decompose them into two separate functions. And so basically to decompose a composite function, you look for an inner function and an outer function. So it's very similar in what I had showed you yesterday, where I said you take the outer function and you kind of set it up like in this part here, you set it up as the scaffolding, and you, in place of the variable, you write a set of parentheses, and then within that parentheses, you write the other function, which goes to the inside. So you want to look for, in these decomposition problems, an outer kind of scaffolding type function and then an inner part that you could maybe pull out and then just replace with a single variable. So looking at the first example that I have here for you, is it says find the functions f of x and g of x such that h of x is 1 over x minus 2. And so as we look at this, the first thing we need to establish is there are going to be two functions, f of x and g of x, and that the composed functions would have been f of g of x like this. So you could see that this g of x is going to be the inner function, and then f of x is going to be the outer function. So looking at our function h of x, we can see there is a set of parentheses, and it's always a safe bet if you have a set of parentheses. Go ahead and look on the inside of that, and you can see we have this x minus 2. So I'm going to leave that highlighted. Same with over the g of x. That x minus 2 is actually going to be our inner function. That is going to be g of x. So this will be x minus 2. Now, what you have to understand is if I took this whole thing out of there, we're left with another function, which is 1 over something squared. Well, in place of what we took out, we're going to just put an x right there. And so that means the outer function, f of x, is going to be 1 over x squared. And there you go. That's how you decompose functions. So hopefully that was pretty straightforward for you. Let's try another one. The other thing that I did want to say is these have more than one correct answer. I'm kind of walking you through the way that I look at these, but there's definitely more than one way to do these. And for instance, this particular problem, you could probably have at least 2, maybe 3 different answers for this. So just keep that in mind. There isn't one correct way to do this. There are multiple. So same deal as the last one. We're going to have two functions, f of x and g of x. And those would have combined as f of g of x like this. And we need to figure out what the inner function was or is, and then pull that out. And so looking at this, there's a couple ways we could approach this. And I'm going to show you 2 different ways we could do this. So I'll put another one right here. So this is 2 different options we could do. The first thing we could do is we could just look inside this cube root and see that there's an 8 minus x right there. And we could say, all right, that 8 minus x is going to be our g of x. So I'm going to go ahead and write 8 minus x for g of x. Now, if I removed all of this out of there, and with that blank space, you do need to have a variable inside there, then the f of x, or the outer structure, would have been the cube root of x over 5, just like that. And you can see if I took this right here and plugged it in, I would get my original function, the one that's composed. Now, I want to show you another way to do this, because there are multiple ways. So rather than looking right here and saying this is the g of x, excuse me, we could say this entire numerator is the g of x. So I could have went and said, all right, g of x is the cube root of 8 minus x. But that means if I got rid of all of that, I would have had to replace it with just a variable, with an x. So that means f of x is just x over 5. So once again, you can see that if depending on what I choose to be g of x, then the f of x is what is basically left after you pull the g of x out. If I took this part right here and plug this in for x, you would see I would get the exact same thing right there. So there are multiple ways to do this, and they're both correct. So that's the thing you have to remember about this. There are more than one correct answer for this. Now, the next thing that I'm going to show you is a quick little clip about domains and ranges and compositions of functions. Okay, so what I wanted you to get from that is to be able to visualize what composed functions are actually doing, because they are a little bit deceptive in understanding that. So when you have f of g of x, PEMDAS tells us you have to work inside the parentheses first. So you're going to evaluate that g of x at a number. You're going to get an output for that number from g of x, and then the output of g of x becomes the input of f of x. And so because the outputs of g of x become the inputs of f of x, it's important to remember that if there are restrictions on the numbers that you can put in for g or f, that those restrictions hold true for the composed function as well, even if stuff seems to simplify and it wouldn't have any restrictions. So as an example, for this one, they want you to find a domain of f of g of x for the following functions. And they have f of x equals x squared minus 9, and then they have g of x is equal to the square root of 9 minus x squared. Now, keep in mind, we've studied and learned how to come up with the domains of functions. And in this class, there are two places where you will have domain restrictions. The first is going to occur if you have a rational function, which means you will have variables on the bottom of a fraction. We do not have that here. But the second instance where we're going to have domain restrictions are going to be functions that have square roots, which we do have here. So looking at the domain of both of these functions, the domain of x squared minus 9 is all real numbers, or negative infinity to infinity. There's no restriction. You can put whatever number you want right in there for x and square it and subtract 9. You're not going to have any issues. But with the square root, we are going to have restrictions because we cannot square root negatives without creating imaginary numbers, which we don't want to do. So what we know to do for these then is to take 9 minus x squared, and we have to set it greater than or equal to 0 because you cannot square root negatives. Now in solving this, I'm going to subtract 9 from both sides. And then I'm going to divide by -1, which gives me x squared is less than or equal to 9. Remember, when you divide by a negative, you need to flip the inequality sign. The next thing we're going to do is we're going to go ahead and take the square root of both sides. And again, when you take the square root, you're going to get two answers. You're going to get less than or equal to 3, or x is greater than or equal to -3. So when you choose the minus of the plus or minus with a square root, you do need to flip the sign over again. And so to graph this is saying x has to be greater than or equal to -3, but it has to be less than or equal to 3. So we're going to get a graph that looks like this: solid dots on -3 and 3 shaded right in the middle. So if I were to write the interval notation of that, it would be a bracket, -3, comma, 3, and then another bracket. So you can see the first function does not have any domain restrictions. The second function does. So we need to keep that in mind. So now I'm going to go ahead and do the composition. So f of g of x is equal to f of x, which is x squared minus 9. And then in place of that, I'm going to do square root of 9 minus x squared, just like that. Okay. Now the square is going to cancel the square root. Boom. Those are gone. Now we have 9 minus x squared minus 9. Well, 9 minus 9 is 0, and we're left with negative x squared, like that. So you can see our composed function is just negative x squared. And you would say, okay, well, that's just a parabola that's flipped upside down, which we should know from our transformations. that's not going to have any domain restrictions. And you would be right if that wasn't a composed function. But because it's a composed function, you need to also consider the domain restrictions of the individual functions that were used to create this composed functions. And so the restrictive nature of these two, this one is the one that is restrictive. So the first one says we can have negative infinity to positive infinity. This one says no, we can only have -3 to 3. So we need to combine those two restrictions and go by the strictest one, which is the domain for this function would still be -3 to 3, even though it looks like it wouldn't have any domain restrictions. You have to go by the function's domains that were used to create that composed function. I'll give you another example of this one. So we have two functions. Once again, we have a square root of x, and then we have x squared plus 4. Now, the square root of x is going to have a domain restriction. That one's easy. You set x greater than or equal to 0, and that's what it is. So that's the domain restriction for this one is 0 to infinity. And remember, 0 it's allowed to be 0 because you're allowed to take the square root of 0. So it's a bracket. Infinity always has a parenthesis. Now, if you look at the second one, it's just a parabola that is shifted up 4. So that would not have any domain restrictions. So that one's negative infinity to infinity. So now that we know this is the most restrictive one, so that is going to be the domain for our composed function, irregardless of what the composed function simplifies down to. So now when I find f of g of x, f is the square root of x, and then g of x is going to go on the inside, x squared plus 4. Now, looking at this, you might be very tempted to write x plus 2. If you do that, that is wrong. Remember the square root. If I take the square root of 9, that gives me 3, which means 3 times 3 equals 9. If I took the square root of x squared plus 4 and I wrote x plus 2, that means if I multiply x plus 2 together, I should get x squared plus 4, but I don't. If I FOIL those together, I get x squared plus 4x plus 4. So what that means is this does not equal x plus 2. Does not equal x plus 2. I can't stress that enough. That is as simplified as it will go. You cannot simplify that anymore. But keep in mind that the x squared plus 4 has to be greater than or equal to 0. Therefore, the domain for this composed function would also be 0 to infinity. Okay, guys, that's what I have for you today. Thanks for listening. And as always, if you have any questions, feel free to email me. Have a great day.